Hey there everyone, so welcome to another video. This one here, an important one on topic of linear regression. That's an important learning module because it's a learning module that will be present not only on the first exam, level 1, but also on the second exam, level 2. Level 1 is going to be a start of linear regression, an introduction to linear regression. That's where we're going to focus only on simple regression. Level 2, we're going to take to the next stage, which is multiple regression. Right? So try to understand as much as you can from linear regression now to make your life easier on the next exam, so you don't have to worry about study too much to understand the concepts that you still need to know. Okay, if you do a comprehensive learning here, a lot of the topics that you see on level 1, on the lessons, on the modules of level 1, the official material, they will appear again on the second exam. Okay, by default or by a understanding here, I would say, look, if I know for a fact that this point is learning outcomes from the level 2 exam, well, I don't know what is the probability that this point would appear on level 1 exam, right? So that's one thing I want to say. However, I always mention that the number of different exams that they have to create now for the level 1 are so large, there's so many, that everything is possible. So everything that's on the lessons official material, you probably could expect as a question or a type of a question in the exam. Said so, let's try to do the best we can to understand linear regression. Okay, it's a very important tool also for financial analysis. All right? Okay, so let's go to the learning outcomes. There you go. So the learning outcomes, right? First one, describe a linear regression model, right? And how the least square criteria is used to estimate regression coefficient and interpret the coefficient. Well, let's go by parts here. What's a linear regression model? It's a linear model, a linear equation that explains the behavior of a variable. Right? It helps you to predict, forecast what the value of a particular variable or scenario will be. That's what a linear regression is. There's always two components on the linear regression, or I mean 3 components, I guess. The independent variable, that's the input. The intercept, that's the value of the regression on the input is 0. And you have the outcome or the independent variable. Excuse me, the dependent variable, the outcome. So dependent variable, independent variable, and the intercept. Those are the 3 names that you need to feel comfortable with. Okay. What is the least square criteria? You know what it is. Let's go by parts here. Least means lower. Square, variance, criteria. So is the minimum variance criteria. Is the minimum error criteria. There you go. So what is a good regression model? Well, it's the regression model that has very small little errors, right? We don't expect that the value that was predicted to be too different from the reality, okay? Least square criteria, okay? So I told you, remove the word squares in statistics and put variance. That helps. I already mentioned the interpretation of the coefficients. Let's see the second one. Explain the assumptions underlying the linear regression and violations, right? Explain the assumptions and violations. That's what the second learning outcome is asking you to know. Well, assumptions, we're going to see here a list of it, but you should know. One of the assumptions of a linear regression is that the error of each prediction is homogeneous. Is exactly the same. It doesn't change. So every time I make a prediction, the error of that prediction with the actual value is the same for each prediction. Okay? That's como homoskedasticity. Okay? That's an assumption. You have to a second assumption, that's a line explain the behavior of the variable. So a line, right? Y equal ax plus b, a line, right? An equation, and a first degree equation is the one that has a x, the x variable, the independent variable. e to the power of 1, for those that remember mathematics from high school. But that's not that necessary, right? So we have some list of assumptions, right? That cannot have some correlation of the error term, right? There's, if it was a multiple regression, you should not have any correlation between the independent variables, right? So it's important that you go over the list of assumptions of linear regression. I predicted that questions could appear from that point, this topic. Point number 3, calculate and interpret measures of fit and formulate, there we go, and formulate, okay, and evaluate test of fit of regression coefficients in a simple linear regression. Look, the concept of fitness of a model will be very well explained and asked you to answer more questions on level 2. Okay, this is just an introduction to what we call the points here, right? This formulate, evaluate regressions coefficients, right? This is a little bit too heavy. So what we need to know here, it's at least to interpret this concept of fitness. What is a fitness, right, for a model? A fit model, it's a model, right, that's adjusted, right, and you don't need to know exactly which adjustments we make in a model to make it fit or to choose the most fit model, right? But understand that a fit model is the model that if you have the least number of the independent variables to explain something is preferable, that's a fit model. Now, it doesn't mean that you cannot have a complex model with several different independent variables explaining something, right? That's, you know, as long as the model has some predictive power, right, then the model could be fit under the prediction, right? So for forecasting purposes, it's a fit model, right? Now, if you prefer some kind of like less small models or like not too complex model, so that's another type of fitness. And on level 2, you're going to learn the measurements that you can use it to kind of find the best fit model. Here is just to understand. Now, when we say calculate and interpret measures of fit, we're going to know the basic ones now, level 1, measures that you can use to see if the model is at least appears to be good. Right? We're going to have to do further investigation, but right now it appears to be good. What's telling me now that the model is fit? For example. Right? That's what it meant. Okay. All right. Next, evaluate test of fit of regression coefficient in a simple regression. Okay. I'm going to show that to you. Follows the same line. Describe the ANOVA table. Okay. Describe the ANOVA table. Look at that. Right. So the ANOVA table is an important tool in linear regression. Okay. Because the ANOVA table will give you a lot of information, the fitness, right? If the coefficients are reasonable, will give you some hypothesis test all in that table. So understanding the ANOVA table, it's very important. And for level 2 also. So try to do a good job here understanding the ANOVA table now. Okay, I'm going to show it to you an example. All right. Calculate and interpret the standard error. I believe now you know how to calculate the standard error, right? Standard deviation divided by square root of n. Calculate and interpret the value for the dependent variable in the prediction interval. So, if you substitute the independent variable in the model, what is the value of the dependent variable? That's one thing you need to know. And bear in mind here, friends, that those models, they could have logarithms, they could be a log model, okay? It could be a linear log model or a log linear model, right? So it's important to understand that. I'll have an examples here for you coming up. What else? Calculate the prediction interval. So the prediction interval is what is the range that the expected value is. We already mentioned that to you, right? The prediction interval, right? The interval of confidence, or also called confidence interval. So the more confidence you want, the larger the interval will be, the less confidence, the smaller, the larger the sample, the smaller the interval, the larger the error or the standard error, the larger the interval, right? So those are the things you need to understand about prediction interval, okay? And describe functional forms or linear regressions. That's what I'm going to show you, all the possible formats of a simple linear regression. Next one. So the summary here, we have a lot of points, okay? So it's kind of like 2 slides of points. So estimation of the simple linear regression model, okay? You should understand that. So introduction, estimating the parameters. You don't need to worry about estimating the parameters, okay? It's possible to do by hands, yes. It's possible to do in a calculator, sure. It takes time. So I don't believe you're gonna have to estimate the parameters. Which parameters are they? The intercept and the independent variable, the one that multiplies the x. I don't think you need to calculate that, but you're going to need to know how to use it and interpret that. Estimating assumptions of the linear regression, I already mentioned that. Which assumptions are they? So let's talk about that, right? So one of the assumptions I mentioned to you, they have to be linear relationship, so-called linearity relationship between the prediction, right? And the independent and dependent variable. They have some kind of linear relationship. Homoskedasticity, right? The key word here is homo, H-O-M-O, means equal, right? The same. So the same error every observation. Independent, so now the predictions are independent, and you have to have the error term has to be normal distributed, which is a strong assumption here, okay, the normality. But anyway, it's important to memorize those 4 assumptions. There could be questions on the assumptions of the linear regression in your exam. Right. Hypothesis test of the linear regression model. What is that? Like I mentioned to you before, we need to test the dependent and the independent, the independent variable, and we need to test the intercept, okay, to make sure that they're not 0. You don't want to have a linear regression that's dependent variable equals 0 plus 0x. Doesn't make any sense. So you need to make sure that the intercept is not 0 and that the coefficient multiplying the independent variable, it's not 0. What do I mean by it's not 0, right? Well, like I mentioned on the video before, in the previous video, you collect your data, you throw in Excel and ask Excel to do the linear regression. Excel come up with linear regression that's equal, for example, y equals 0.05 plus 0.003x. Look, 0.05 is close to 0. 0.003, it's close to 0. So because we have a lot of, it's data analysis, it's not perfect, I need to test if it is indeed 0.05 and if it's indeed 0.003, meaning as long as it's not 0, the regression can work. But if both are 0, or one of them is 0, then it might not work. Okay? That's why you have to do the hypothesis test on the linear regression. Well, analysis of variance, it's the ANOVA table that you're talking about. Look, ANOVA stands for analysis of variance. ANOVA, right? ANOVA, analysis of variance. So that on the ANOVA table is going to tell you exactly where is the analysis of variance. When you arrive there, I will explain to you. Measures of goodness of fit, to see if the linear regression is good, or in this case maybe preliminarily good. We're not going to go over all the methods that we have to test fitness of the model, right? We're just going to kind of talk about some of them. What else? We have more. We have one more set here. There we go. So the hypothesis for the individual regression coefficients, which ones I mentioned. Prediction of the simple linear regression model, that's using, substituting the independent variable, finding the dependent variable. The ANOVA table, in the standard error of the estimate. We're going to talk about that when I show the ANOVA table. Prediction using a simple regression. So again, look, the P and the M, right? It's very similar, right? The learning outcomes. Functional forms of simple linear regression. So how the linear regression could, the simple linear regression could appear, okay? And those are the R, S, and T points here are precisely some formats of the linear regression model. It could be in a log-lin model. It could be a lin-log, right? It could be a log-log, and it could be a lin-lin model, right? Linear model. Okay. When you see the examples, I think will make more sense if it's not making sense now. All right. Selecting the correct functional form. So if you have to select what is the best linear regression, right, among several, maybe they could ask this question. They give you 3 linear regression, they give information about each one, and you have to decide which one is the fit one, right? And you're gonna get that by understanding the measures of fitness, or the tools that we have to identify if this regression is good or bad. Okay. All right. Reminding you, we're doing a preliminary analysis. Okay. So this is a preliminary analysis on the regression. We're not going to go too deep. Level 2, you're going to go deeper, because level 2, you're going to have to do several tests to make sure that that model is good. And when I say good, is that model is fit, that model has prediction power, right? That model can be used, that model has statistical meaning, economic meaning, okay? So it is a model that we can use. We have several examples out there, friends, right? We have the Fama-French model, very famous model, okay? We have the CAPM, capital asset pricing model. It's a regression model. It's a simple regression model, the CAPM, capital asset pricing model, which is a topic you need to know for level 1, okay? All right, so let's see what I have prepared here on my notes. There we go. Oh, it's a little out of focus here. There we go. One more, just one more. Perfect. All right, so there we go. Those here are the learning outcomes I'm highlighting. So again, right, take a look. Those below here are the key points, which you just covered. And now we're going to go through the points I made here. All right, let's go. So I'm going to explain those 3 points here first. Estimation of the simple linear regression model, introduction to the linear regression, and estimating the parameters of the regression. The thing is, this is all done using some kind of software. Excel does that. So you highlight, right, one column, highlight in another column, right? And then you press the data tool pack set that we have on Excel. It's an add-on for most of us. You have to add that, and then that's it, right? And then the what you see, the relationships will be transformed into a ANOVA table, which is coming further below here, right, on my notes to show it to you. Okay, so how you estimate the simple linear regression model? Again, I don't know how many of you have done that. I have, right? Because when I learned this long time ago, we did have calculators when I was in the university, obviously, but we didn't have, it was in the 90s, so we didn't have much, the softwares that we have available now. So a lot of those linear regression problems we had to do by hands. Right? So calculating the difference and the squares and add and put in a formula. Oh, that's the intercept. Then you do it again, and then you find the coefficient of the independent variable. Then you create the linear regression. We don't need to do that anymore, and I doubt you're gonna have to do that for the exam. All right. So how to estimate the parameters of the linear regression? Again, we're gonna use that software called the ANOVA pack, or the data set linear regression analysis tool. There's like several different names for the softwares that do that for us. Good. So continue here. Look, I put it here, a basic format of a linear regression, simple regression. Simple because there's only one x variable, right? One independent variable. If I had multiple independent variables, then I have a multiple regression. Can you think about a single regression model in real life? Sure, I just gave one. CAPM, okay? CAPM, capital asset pricing model, okay? That's a single regression, or linear single regression model because there's only one independent variable, okay? What is the independent variable, the CAPM? Beta. Beta is the independent variable of the CAPM. And you have others that have more than one variable to explain. So you have, for example, the Fama-French model. The Fama-French model is the CAPM plus two independent factors to explain the return. CAPM explains the return on a stock. Well, how? It takes the risk-free rate and the market risk premium. So if you don't know CAPM, you will know, because you have to know CAPM. So I'm kind of like introducing to the capital asset pricing model now. Now, the Fama-French model is you don't need to know for level 1. You need to know the Fama-French model for level 2. But the Fama-French model is a multiple regression model, has 3 variables, right? And 3 independent variables. One of the variables is the same as the CAPM, the market premium. And then you also have a size, right, premium, and then a value premium or sensitivity, to predict the value, the expected return on a stock. Don't worry about the Fama-French model for the level 1, okay? That's not a problem. Just put here as an example of multiple regression. Worry about CAPM, not for QM. You're probably not going to even see capital asset pricing model in the QM. You will see this in corporate finance or corporate issuers now, and portfolio management, some equity questions as well. So CAPM is like, it's a must-know, okay? It's a must-know, capital asset pricing model. Right, very well. So, well, let's back here. The capital asset pricing model will have this kind of like way here. Why the dependent variable on the CAPM is the expected return on a stock. So look at that, expected return equal AX plus B. Look, I'm going to put the CAPM here for those that are not very familiar with. CAPM means the expected return. I'm putting in capital letters here. The expected return of a stock equals the risk-free rate plus the beta of the stock times the market premium. That's, look at that. This is CAPM, okay? Let me put this a little bit. There we go. So look at that. Very important that you understand this, but not for now. But I can show it to you. Look at it. Risk-free is the equivalent to that B on my equation. Beta times premium is the AX there, right? So there you go. The CAPM is indeed a linear regression format model. Very well. So look, who is changing on the CAPM? Beta. Each company has a beta. If you don't know what beta is, I'm just, for now, it's the risk that the stock is in relation to the market which it trades. So if the market goes up 1% and the stock, every time that the market goes up 1%, that stock goes up 1.5%, or 50% more, you can say that the beta of that company or that stock is 1.5. Right? So because it responds 50% more than the market does. That's the concept of beta. Beta sensitivity, as we say. The higher the beta, right, the more the expected return, because beta is a risk factor, right? It's a risk factor. It's the risk of the stock perform way above the market, but also the risk of the stock perform way below the market. Right? That's CAPM. Good. So now we can remove it, because we're not talking about CAPM here, right, friends? We're talking about linear regression, right? So that's the format. So you can make predictions, right? You can make the predictions of the that you need using a good model. If the model is good, then you can use to make predictions. That's the whole idea. Right? Look, if you're going for a PhD thesis, you probably, most of you are going to end up doing some kind of regression model as part of your thesis. Right? It's very common, this, in graduate studies. All right, let's go here. Now, friends, I'm going to talk about here some of the basic points about linear regression. So take a look. Linear regression is this one here that I'm highlighting, or that kind of like showing in the mouse here. So I have several points. Look at that, several points. That's my scatter plot. Remember the scatter plot that I showed you in a previous video? There you go. Now I put a line in the middle here. Boom. That line explains the behavior of the x and y variable. So imagine the x on the x-axis and the y on the y-axis. Look at that. I have the x is increasing and the y is also increasing. That's what the line's telling me. Okay. Now on top of the line I have those little dots. Okay. Those dots are the real values, and the green line is the prediction value. So notice that there is a distance between the real one, which is the dot, and the line. So you can make a little distance here. Take a look, like a little distance. Okay. Notice that that distance, which we call the error, it's small and pretty much the same. Right? When you say pretty much the same, it's not they have to be identical, right? When you say homogeneity, means pretty much the same. Right? So that would be a good regression. Now I have two images here with the blue line here. And apologies, what here is not very clear, but here is written homoskedasticity versus heteroskedasticity. Okay? Heteroskedasticity you don't want. You wanted the homoskedasticity, means you wanted the error term to be equal along the line. Okay? So that's what you have here on this little one here. See that all those little dots? They're very close to the blue line. Right? The distance is pretty much the same. Now over here, you can see that they are not the same distance. You see that the dots here in the end, they have a higher distance to the blue line than the points over here. That's heteroskedasticity, and this is a violation of the linear regression, and this will not be a good fit model. The model that exhibits heteroskedasticity will not be a good model, a good predictor model, and you cannot use. Then what do? Increase the sample, change some of the assumptions, do something, but this cannot proceed. This one you can. Okay? There you go. So now let's see if you can digest some information here. I'm going to talk about the ANOVA table. Okay? Look at the ANOVA table here. Okay? That's an ANOVA table. Now I have it in a little bit larger format here. There you go. Because I want you to see it there. Now, friends, let's try to digest this table. And then let's take a look on this box in green here to see which type of questions you can answer by looking at the table, right? Because if you get something like that in the exam, they give you the table or they give you a partial of a table and they're going to ask you some questions, right? Usually those questions, for those that know, for those that had to prepare, it will be easy. You take a look at the table and know exactly where the number is. Or take a look at the table and know exactly which calculation you have to do. So let's try to digest the table first, and then we go over those questions here, okay? So look at that. That's the same table here, okay, without those questions. So you have 3 points, 3 portions of that table here. This one, called regression statistics. The second one, this one in the middle, is called the ANOVA. And the third one, which is the regression coefficients. Okay, so the regression coefficients are in the third one. The analysis of variance of the regression is on the second one, and the regression per se, the fitness and others are right here on top. Now I'm going to go to the other picture, which is a little bit like more visible to see those numbers. Take a look. Let's talk about the first portion here. First portion. I have multiple R square, adjusted R square, standard error, and observations. So what they mean? So what is the multiple R? Multiple R is the correlation between X and Y. Okay? Means 0.34. R square it's 0.117. What is R squared? R squared is called the coefficient of determination. Coefficient determination is the explanatory power of the x variable over the y variable, meaning how much the independent explain the dependent. In this case, 11.77%. So there is an explanation power, but it's not close to 100%. Okay? All right. If you take the square root of the R squared, you get the single R, which is the correlation between the variables. Okay? The adjusted R squared, don't worry about level 1. Adjusted R squared, it's the prediction power that you get, right? If you make some adjustments, usually not the case here, but usually if you keep adding more independent variables, you're gonna have the adjusted R squared changing. But forget about the adjusted R squared. The standard error is not very relevant here. The observations, well, maybe. The most important ones are the multiple R and the R squared. All right, now, second portion of the table down here. ANOVA. I have regression, residual, and total. So memorize that. Regression means good. Residual means error, means bad. Regression is good. That's good. Good in terms of something's being explained by. So the dependent variable is explaining the dependent variable. That's the regression. And the residual is the errors, the amount of errors that you have there. Now, let's talk about these degrees of freedom. Degrees of freedom for the regression is the number of independent variables. In this case, only one. Take a look. It's a simple regression. The total that you see here is n minus 1. See, the n is 62. Number of observations. N minus 1 is 61. And the number in the middle is the number that you throw there to make this one plus that equals 61. So 1 plus 60, 61. Those are the degrees of freedom for the regression, for the residual, and the total. Now the other column here, SS, okay? Sum of squares. Sum of squares is variance. So look at that, the variance of the regression. It's 1.02796, etc. That's the sum, the variance of the regression. The variance of the residuals, it's 7.7. And the total variance, it's 8.7. Okay? Question, what does it tell you this, right? What is having the regression squared, the variance of the regression, the variance of the residual tells you? It tells you the following. If the large amount of residuals, the large amount of variance, larger amount of variance comes from the regression, that's a good sign. That means that the variance is being caused by the change in x. Right? The change in dependent variable is changing my dependent variable. That's exactly what I want. So, meaning, right? It's like, for example, if you take orange juice every day, right? Will you have an impact or not on your health? I don't know. Maybe, maybe not. How do I know that? Maybe I could do a test like that and see if the intake of OJ is going to help you somehow, right? Somewhere you're going to be more, produce more, you're going to be more attentive, you're going to sleep less. I don't know. Something that you try to prove here, right? Now, if the sum of the square, the variance of the regression that you use to measure the intake of OJ giving some kind of benefit to the person, if the sum of the squares of that regression is very high, then you're in the right target. Say, hold on a sec, that's something here telling me the OJ, it's really causing something positive on that person, on that group that you analyze. That's the same idea here. Here we have that is actually a finance model, right? So it's a finance model trying to predict here. If you see down here, called spending. So maybe you can say like the GDP or change in GDP, actually the change in GDP as caused by spending, right? For example. Actually, it's not going to work because here the coefficient is negative, right? So spending causing something. So the more we spend, the more something happen here. So let's see something that we spend, and then you kind of shrink, right? So let's say the private sector, okay? That's because you're going to learn that in economics, something called crowding out. Crowding out. Let me use crowding out here to exemplify what's going on here, since I choose spending intercept here for the regression. So imagine that the government spending. Okay, when the government spends more, if it spends too much, it may hurt the private sector. So the private sector spending will go down. The investments on private sector will go down if the government starts spending too much. We're going to talk about that in economics. But imagine that that's what it is. So I have spending as a function to predict spending on the private sector. Government spending impacting private investments. Let's think about that. Good. So now I have private investments equal to 3.40820858 minus 0.000584873 times X, which is the spending. So every time that I increase the spending, I multiply by minus 0.0058, add 3.4, and that's how much the private sector has spent in that scenario, or the decrease, increase, whatever you're trying to measure. Good. Now let's go back to the second table. So now I have a scenario that the sum of squares, the variance of the regression is 1.03, rounding. The variance of the error is 7.7. The total variance is 8.7. So think with me here. If I take, let's put it right below me here. Is that good? There you go. Let's put it right here, okay? To see it. Imagine now, so let's try to do a calculation here. Let me take the good variance, right? The variance of the regression, which is equal to 1.027. Well, let's say 28. And let me divide that, okay? Let me divide that by the total, 8.73. 8.73. Look what happened. I got 0.12. And if I kind of like increase the number of decimals here, look what I get, friends. 0.1172. It's exactly that number there, 0.1172. Okay, kind of close enough because I rounded. So what I proved here or showed here to you is that the coefficient of determination, the R squared, the explanatory power of X over Y, it's calculated this way. You take the sum of the squares, the good variance, and you divide it by the total variance. Okay, so 11.72% of the dependent variable is explained by spending, which is the independent variable. There we go. Now, continue here on the ANOVA table. The mean variance, that's called mean of squares. The average squares, the average variance. So the average variance for the regression is 1.02796 divided by the degrees of freedom, the number in front. So if I take that and divide it by degrees of freedom, I get exactly the same number because degrees of freedom is 1. But take a look on the regression, the sum of the variance, the sum of squares of the residual, the variance of the error, right? Now, to do the average, I'll divide it by 60, the number in front of it, the degrees of freedom. And then I get 0.128. That's called the mean variance for the regression and the mean variance for the residual. Guess what? I'm going to divide it one by the other. You're going to divide it one by the other, and you're going to get the next number here. It is 8.0056, etc. It's the MS regression divided by the mean variance or mean square residual. Get the F. That F is your F test that we saw previously. What does it mean, right? If this is a hypothesis test, and then you did a hypothesis test and the F come up with 8. Let's say this 8 is way above the critical value that you have predetermined. What is your conclusion? What is your conclusion if the F test, your F test is higher than the critical value? The answer is that the F has, the regression has explanatory power. Then you can reject the hypothesis, the X does not explain Y. Because if X did not explain Y, then your F would be very small. Obviously, because if I divide, look, I'm dividing the average of the good variance divided by the average of the bad variance. If the average of the bad variance is very large, my F is very small. And that's exactly what it means that doesn't have a prediction power. If the error term is too much, there's too much residuals, then it's that there's not explanatory power. Then my F test will be saying that you should fail to reject that there is explanatory power. Okay, fail to reject. So fail to reject, right? So you kind of conclude that there is no prediction. X, it's not predicting Y in a good way. It's not a good fit, let's say. All right. Now, if you don't have the critical value, don't worry. Take a look on the significance of F. And if it's below 5%, then it's good. You can reject any hypothesis for a tiny, this is the p-value of the F test. So you can, look, this is 0.006. So it's very tiny. You can safely reject any hypothesis, okay? So you reject hypothesis, friend, when the test F or T is very high, or when the p-value, the significance, it's very tiny, okay? And that's what I have here, both. Good? Well, let's go to the third portion of the table, and then answer those questions in the rectangles here. The third part is the components of your regression, which is the intercept and the independent variable. Okay? Now, I need to do the hypothesis that the intercept is not zero. I want to reject that's zero. And the spending, I want to reject and zero. Now, do you remember the formula for the t-test? Because this is an expected value, right? I expect the intercept not to be zero. It's expect. So I need to do a t-test, right? Or a t-statistics, or a t-distribution, let's say. Okay? All right, a t-test. How we do the t-test? I said to you on the previous video, you need to remember two formulas. One is the test of correlation, right? R square root of n minus 2 divided by square root of 1 minus r squared. That's the test for correlation. We're not doing correlation. We're doing expectation. So we're going to do that one as the difference. Remember the difference of the mean, the expected value minus my hypothesis divided by the standard error. That's exactly what I'm going to do here. So think with me here. Look at that. What is my expected value for the intercept? It's 3.408. I'm just going to round it. I'm going to put 3.4. Minus, what is the value of my hypothesis? Well, my hypothesis is that I want to test for zero. I want to reject that they are zero. So put a zero there. And then you're going to divide that by the standard error, which in this case is right there, 0.1095388817. You see that number? That's the standard error. I'm going to round it for 0.1095. Okay, 0.1095. Great. There we go. That's my t-stats. That's my statistics. And if this number is higher than the critical value, I will reject the hypothesis, right? The answer here is 31.14. Wow, you're good in mathematics. Not really. I mean, honestly, actually I am. But I mean, not to the point to have this fast brain to do those calculations. It's because I knew the number was right there, right? 31.114. Okay, 31.114. That's exactly the t-test. So I don't need to do this calculation in the exam. The ANOVA table will do it for you. Just take a look. Okay. Now, what do you think about the 31.11? Do you need a critical value to figure it out if you're going to reject the hypothesis or not? No. This number is way above 3, right? It's 31. Rejected anything. So here we conclude that the intercept is significant different than 0 because we reject the hypothesis that is 0. Second one for spending, same logic. Take the expected value is negative 0.00058 minus 0 divided by the standard error that this guy here, 0.0000267. Don't need to do the calculation. It's right there. 2.83. 2.83. Forget the negative sign. What do you think about 2.83? It's so close to 3. It's so close to number 3 standard deviation, right? That you, if you know if it's above 3, you're going to reject it. It's so close to 3 that you could safely say, no, I'm going to reject the hypothesis that spending is 0 because this number is 283, but you need more. 283 could be borderline. So you need a critical value. Oh, I don't have the critical value. Well, take a look on the p-value. Is the p-value lower than 5% or 2.5% if it's 2 tails? It is. The p-value is 0.0006. It's a very tiny p-value. Then you can reject the hypothesis that the spending coefficient equals 0. There we go, friends. That's the ANOVA table. And any one of those things that I just said here to you, the F-test, the coefficient of determination, the R-square, all of this could be a question in the exam. That's why I selected those typical questions here in this rectangle for you, this green rectangle there. So look at this. Find the regression on the table. Okay, find the regression. That could be a question. Okay, find, according to the ANOVA table, the regression is, then the answer is right there. 3.408 minus 0.000058x. That's it. That's your regression. Now, second question. What is the percentage of the y variable explained by the x variable? You don't need to do the calculation. The ANOVA table has the answer. Answer, 11.77% is the R-square. So be prepared that some of the questions might require you just to look at the table and take the number and answer. Okay? Matter of fact, take a look on the answers. When you see 3 answers, try to locate those numbers on the ANOVA table. Or if it was a different type of question, sometimes the number might be at the table. So, okay, that's a clue for you. All right. Confirm that the F equals 8.00566. How we do that? How we confirm that the F is 8? Well, I divided the 1.027964906 by 0.128. I get 8.00 and change. That's how you confirm the F. So you divided the MS, the mean square regression, you divide it by the mean square residual to get the F-test. All right. Is F significant? What does it mean? Yes, the F is significant because it's 8, which has a very low... So now be careful here, because at least for me, it's confusing, or was before I learned my statistics. When I was learning statistics, right in the beginning, it kind of confused me as the following. Significance of F is very small, means good. So I don't like the word significance of F here. I just like p-value of F. The p-value of F is 0.6 because is statistics significant if the p-value is small. Okay, so it is statistics significant because the F-test is very high. That's statistics significant. The p-value, this number here, it's very tiny. That's significant in this statistic point. So there is explanatory power. Okay, so F means that the independent variable has some kind of explanatory power over the dependent variable. We don't know how much. F-test is not telling you how much. The F-test is telling you that there is a relationship. So the X helps to explain Y. The OJ, that orange juice, is helping to explain that good benefit on that person. we need to go further to see how much. Okay, there we go. Calculate the change in GDP if spending is 1,000, right? So if the spending is 1,000, right? What would you gonna do? Okay. So that's the answer. I already answered my first question. This is change in GDP due to the change in spending. Okay. I was gonna ask myself why is negative, because sometimes if the government spends more, then GDP has to grow, because that's one of the main premises of the GDP equation. The more the government spends, the more we could grow. But anyhow, let's not question that. We just focus on the linear regression here. So all you have to do here, friends, is substitute. I hope I have space here. Let's down here. We substitute here, right? You're gonna do equal. If you have Excel, you would 3 point. I'm gonna round those numbers. 3.408 minus 0. Be careful with the minus, huh? Don't forget that. 1, 2, 3 zeros, 585 times 1,000, right? Because that's the value given there, 1,000. Yes, you could face a simple question or substitution on the linear regression to find the answer in the exam. Sure. There you go. Then this would be in billions or trillions and millions, and that's the change in the GDP due to the change in spending. There you go. All right, simple. Now, how could you complicate that? Well, you could put a log-ln equation, a ln-log equation, a log-log. But those ones I will explain further down. What else we need to explain here? The last one. Are the intercept in the independent variable significant different than 0? We just proved that it is. Because you can take a look on the t-stats. And the t-stats here is 31. Reject the intercept is 0. 2.83. Now p-value very tiny. Reject the spending coefficient is equal to 0. There you go. Those are the type of questions that you could be asked in the exam. I mean, more than those, obviously. You could have, like, I don't know, I cannot predict how many questions you're going to have. Now you're going to get it. But that could be some of those that I gave it to you could be candidates to be questions in the exam. All right, let's continue here now. Okay, there's a lot of points. You saw there's a lot of key points. So it's a longer video to explain everything here, right? In a good way, without, rushing or anything like that. All right, friends, let's see here. Measures of goodness of fit. The hypothesis of individual regression coefficients, we already did that, actually. Prediction in the simple linear model, we already did that. Is substituting the x variable for a number and finding y. The ANOVA, we already explained that to you. And the prediction using simple regression and intervals, right? We're going to talk about that. All right. So we already explained to you the coefficient of determination, the R square. Okay. I already explained to you that the sum of squares means variance. Right? So the correlation, the coefficient of correlation R, okay, or multiple R, is the square root of the R2. So those are questions that could be in the exam. So I'm just kind of like giving to you. I already explained to you the F-stats, right? The F-stats, which is the ratio of two variances, the good variance, the explanatory variance divided by the residual variance. That's what the F-test is, okay? And that's explained here, all those points that I kind of like explain it to you, okay? How to get the mean square regression, right? And how to get the F, as I covered on the ANOVA table. Right. Prediction interval, right? Using the estimate coefficient, the standard error of the estimate coefficient, and the critical value of the t-distribution, find the interval, right? So look, it could be a question that you have to calculate the confidence interval in the exam. So look, I don't think it's difficult, right? You need to memorize the concept here. You are always going to have an expected value. Oh, what's going on here? Oh. It's because it's not on the color that I want. There you go. I'm going to finish this. I'm going to explain it to you. There you go. So let's say, friends, you have an expected return here. Okay, that's your expectation. Let's say your expected return equals 5%. That's your expectation. Now, could be 5% plus something, or could be 5% minus something. Look at that. Something minus 5% and something plus 5%. Those are the upper bound and lower bound of your interval. The lower number, the highest number in that interval. So it's the average plus a number and the average minus that number. What is that number? That number is critical value times standard error. I'm actually going to put CV here. CV times the error. Okay, look at that. Critical value times the error. Critical value 2.5, the error 0.3. Multiply, that's the number that you're going to add on the mean, subtract from the mean to get the interval. That's it. So let's say a coefficient or critical value 2.2. An error term, right, 0.5. Or standard error, okay? This is not the standard deviation, the standard error. 1.1, okay? So let's say this was in percentage. So let's see my interval here would be 5 minus 1.1. There you go. Didn't work because I did not put the minus, right? Look at that, 3.9, okay? That's the lower bound. And then I do 5 plus 1.1, which is 6.1. And then I have my confidence interval here, which goes from 3.9, 5 is here, right? And 6.1, it's here. Put a percentage there. So there you go. That's an interval. Goes from 3.9 to 5.61 with my average in the middle. Okay, so all you need to remember here, in case you get a question that you have to compute the interval, is remember critical value times standard error is the component that you add and subtract in the mean to get the answer. Very good. I hope you're doing good here. Approaching to the end now, friends. Okay, now the forms, the violations and the assumptions. See, I showed you a list of assumptions. Let's see again the list of assumptions. There we go. Linearity, homoscedasticity, independence, normality. Okay, those are the assumptions. Now, I could have some kind of violations on the assumption. For example, the relationship's not linear. That's a violation. Or the error term, it's not the same. Okay, it varies. Okay, so those are the violations. Level 2 is going to ask you more about violations, right? Because you're going to have to test to see if there are those violations are present on your regression, not level 1. Level 1, you just need to know which violations we're talking about here. All right, so the assumption is linear regression. If it's not linear, well, then you have to adjust it to make sure that the relationship is linear or find another sample. Homoscedasticity, variance of the error term is the same. And if it's not the same, there are ways to fix it. You're going to learn that on level 2. Okay? The independence is that the error term has zero correlation. There's no correlation with the error. Meaning, this error is 1, the next is 2, the next then 3, 4, 5. See, they're correlated. The more I increase x, the more my error term increase in the same proportion. That's a violation of the assumptions, right? This is not, you cannot have a regression model when the error terms correlated with each other. Right? They always are increasing similarly, right? So that's a violation. And if the errors are not normally distributed, right? If the values of those errors are not in a normal distribution, those are the assumptions. Try to memorize them, okay? Because there could be questions about the assumptions. Now, my last key point, the types of models, right there, friends, right here, okay? Let's talk about that. The log-lin, lin-log, log-log, okay? We don't have, well, we have a lean model, linear, okay? So take a look, it's so simple. The first name is for the dependent variable. The second name regards the regression, okay? So log lean is this, look, as the name says, log lean. I'm gonna make more, give myself more space here to work a little bit. There you go. That's good. Now, look at this. The name says all, right? Look, it's a log lean. See, think about y equals b plus ax. Think about that, right? So if it's in this case, let's now apply what's written there in terms of log. See, it's log lean, so the log goes on the y. So a log lean regression is this one here, is the ln of y equals intercept plus, there you go, look at that, ln, or the log, linear, that's the natural log, right? The natural log of y equals b, intercept plus ax, there you go. This is a log lean. Now what about the lean log? See, the lean log, the log is on the second term. The second term is what's after the equal sign. So a lean log, it means equal, it means y equal b plus the ln of x. There you go. That's a lean log model, right? It starts with, the log is on the dependent variable. And the log, well, the log is both logs, right? So I have to put a ln here. And there you go. Let's put the ln in small letter. There you go. Log. A log here and a log there. That's it. Okay. So what you need to know now is if you get one of those types of linear regression that has the log on it, that you know how to solve, right? That's basic math. That's part of the prerequisites. Know how to use the calculator to find the value of a log of y, right? So it's the ln. Okay, that's it. I guess that's it. Yep. The next video is going to be the last one, intro to big data analysis, but let's do a recap on the linear regression, okay? Because there's a lot of points we discuss here. So I'm going to go to the key points. Estimation of the simple regression model. I don't think you need to worry about estimating the parameters, okay? But know what it is, now what the parameters are in it, the idea behind linear regression. The assumptions of the linear regression, okay, the linearity, homoscedasticity, independence, and normality. By the way, those three, the assumptions 2, 3, and 4, are related to the error term. Okay, the hypothesis test regarding linear regression for the intercept, for the independent variable. Okay, the analysis of variance, or the ANOVA, not part of the ANOVA table. Measures of fitness. We only saw the R square and the F stats. Okay, you're going to see more on level 2. Okay, prediction in the simple regression. It's just replacing the independent variable and find the dependent variable. Be careful with log models, not logarithmal models. Okay, the ANOVA table. And the types of models here, right? The log lean, the lean log, log, etc. Okay, there you go. I think that's good enough. I think that we addressed all the points on linear regression, right? So, wow, a little change here. There you go. So I guess we're done. Okay, we explained all the learning objectives, the learning outcomes, key points. Now it's your turn to practice. Now, there are a lot of questions you can ask about linear regression. That's true. There are a lot of possibilities because there's a lot of material, okay? But remember, linear regression will be on level 2 as well, okay? So here, I assume, is going to be basic questions about linear regression, okay? And therefore, I don't think it will be the star of the quantitative methods exam linear regression questions, but definitely expect a few linear regression questions in the exam. I would not expect something too complex or not too difficult to answer. So do a good job understanding the concepts, right, that we explain here for you today. All right, that's it, friends. That's the end of the video. Bye-bye.